To achieve that, we must consider the completely generic case. So we have to tackle the case of three reflections in lines which are neither concurrent nor parallel. And so far we only considered, aside from concurrent or parallel lines, only the case when two of them have a common perpendicular. But in fact, that's enough. So the next step is we are going to show that so the goal is to show that a product of reflections in three lines which are neither concurrent nor parallel is a glide reflection. Goal composition of reflections in three lines which are neither concurrent nor parallel is a glide reflection. Okay, again, it's a good point for you to pause the recording and try and prove it on your own. Well, maybe this one is a little tough. We will come back with the explanation in a few minutes, but first let's understand glide reflections in a little bit more depth by thinking about the properties. So let's, again, we're interested, it's basically an algebra course hiding under the name of geometry. So we have to try and figure out algebraic properties of glide reflections. So, of course, the first question is, do they form a group? What do you think? What do we have to check? Inverse property, so algebra of glide reflections. So as far as group property, inverse property we have to check first. So can we say that any inverse of a glide reflection is a glide reflection? What do you think? Well, we have just seen before that any glide reflection can be written as a product of half-turn and a reflection. So let's say sigma p, sigma l. And we can write it in a different order as well. So what would be the inverse? So any gamma, any glide reflection gamma can be written like this. So let's calculate the inverse of gamma. Would you? What is going to be? Correct? Sigma p, sigma l. So also a composition of a reflection and a half-turn just in a different order, but we know that this is also a glide reflection. Not the same as the original, of course, but it's also a glide reflection. So inverse property holds. Checks out. So what do you think? Are we going to come up with a group of glide reflections or not? Okay. What about the closure property then? So what happens if we multiply two glide reflections together? Say gamma 1 times gamma 2, or compose, rather. What can we say about the product? Oh, well, what kind of transformations, what kind of isometries are glide reflections? So they are products of three reflections, they are even or odd. Right, odd. So if you multiply odd by odd, we will get even. So unfortunately, this can't possibly be a glide reflection. Well, that's too bad. So set of all glide reflections is not a group. We're interested in groups here. What can we consider as far as groups go? Let's consider a group generated by a single glide reflection. So for the whole set of glide reflections, so they are not a group, glide reflections collectively do not form a group, since the closure property fails. But let's consider a group generated by a single glide reflection. So what happens if we consider this group, where gamma is glide reflection? What can we say about this group? First of all, is it finite to infinite? What do you think? Correct, it is infinite. How do we show that? So we can say it's infinite cyclic group. Are you sure it's infinite? What's the easiest way to prove it? Well, if you think about it, what this does is it has inside, so some of those products of gammas that we have inside will turn out to be translations, just like gamma squared. So gamma squared, well, if we write it as sigma A, sigma B, sigma C squared, then what will we have? We know that sigma C can commute, and we will have just can commute with this. So sigma C will finally meet each other and annihilate, so we'll just have the product of this translation, sigma A, sigma B squared. So fill in this blank, check that this is correct, and that's clearly a translation. So it will be a translation which is 4 times the directed distance from A to B, and then we know that inside, so if we consider inside the cyclic group generated by gamma all possible powers of gamma squared, and we know that's a non-trivial translation, a non-identity translation. So this is a subgroup of our cyclic group gamma, and it's generated by a non-identity translation. That means it's infinite. Non-identity translations tend to form infinite cyclic groups. So if inside our gamma we have infinite cyclic group of translations, it must mean that this itself is infinite. So this typically I think about it as this Winnie Pooh steps. So Winnie the Pooh group. And so on. So we have from here to here we go with gamma squared, but here we flip also, so this is gamma glide reflection, this is gamma glide reflection, but between each right footsteps and left footsteps we have gamma squared, group generated by gamma squared acting